Now, a lot of what you can test the assumptions, a lot of them you can only test them after you run the model. So I'm going to go in here and then I'm going to show those examples. So we already discussed this to some extent. So the Cook's distance on the back end is running the model with and running the model without. I'm not going to get into the math of this, but this is the code that you use to find a Cook's distance. Excuse me. This code produces a graph that's showing the influential data points. So this data point causes the results to change quite a bit. So I would call that an extreme outlier. So we should remove this value because it's influencing our model. So 1758, how do we know which one? So if we go in, there are row names over here in R. They're always, so it's kind of like an ID variable. 1758, there's a way to do this programmatically, but I wanted to show it this way as well. So 1758, here we see this. So we could have this number go in and find 1758. It's Story County, Nevada. That's the one that we want to remove. You can do this programmatically using your row names and indexing if you would like. And I actually even made a typo. Story County, Nevada. That's what we want to get rid of. So these are the things that you would always want to go in and check, look for those issues before you would turn in results. So now we're going to remove that, and we now have a linear model small. That is our new value. So I am now going to rerun our model. So I'm going to come up. So just removing that one data point, our coefficient changed from 1.408 to 1.51. So for one data point, that is a very large change in our coefficient, and that shows you exactly why you want to remove outliers. One data point should not change the results that much. So that is Cook's distance, checking for outliers. We discussed this, and I'm going to blow this up a little bit, when we looked at the simpler statistical tests. So we are looking at the distribution between, this is a QQ plot, basically. So we have our T quantiles down here, so that's a standardized value. And then we have, for this particular model, these are the studentized residuals, so they have to do with the error values. The assumption in this case is that the errors are normally distributed. So the error values coming from your model are normally distributed, not your input variables. So what this tells you is if your errors from your model are normally distributed. If you see, and this isn't perfect, that's why I wanted to blow it up. This is slightly off at the end here, and this is pretty well between the bounds, but if this follows a pretty straight line, you should be good to go. If you see an S pattern, that's bad. If you see something that looks like this, that's bad too. Those both indicate that you cannot use a linear regression. So keep that in mind. That is the QQ plot. So one thing that is really neat about R, and I am going to run this, with linear regression, you can use that piece of code and it creates a lot of the different graphs that you can look at this all at the same time. I created the QQ plot on its own so it could be more easily visible. You would probably want to export this to look at the details, but that's just a different view of what we've already seen. And now we are going to look at a couple other things. So these two values give us some information about homoscedasticity. Remember that this is equal variances. So variances have to be equal or homogeneous. And then In order to do that, we are again looking at our error values. That's also called the residuals. So basically what our model does not explain, that difference between our actuals and our predicted models. So what you want to see in this case, and that graph chart shows us exactly what I showed you before. So this is the left graphs you're seeing here. So they're on the left-hand side on the top and bottom. You want to see a relatively straight line here and also here as well. The other thing that you want to see is that the width here is not all that different from the width here. So you see that if you saw a really narrow range here and a much larger range here, that would indicate that there's a problem. But we're seeing something that looks pretty homogeneous here. On both sides, it looks similar. We're seeing that over here as well. Both of these are, this is the residuals. This is the standardized residuals. So again, I'm not going to get into the math, but these standardized residuals are just going to put it all in the same scale. So that gives a very similar piece of information, just standardized. So we're seeing again here something that looks like this side looks pretty similar to this side. If you're kind of looking for this height here, if there's a height difference on one side versus the other, then you have a problem. Now we're going to look at the linearity. This plot, and I'll show it in the code in a second. You want to, in this case, check to see that this red line approximately follows the dashed line behind it. It's a little hard to see in this case. But this needs to be pretty straight is the point. So this helps you test whether your data is linear or not. If the data is quadratic, again, or logarithmic, basically it follows a pattern. If your line looks like this, then you can't run a linear regression without having biased results. And that I originally used a different value. So going back into our code. So this explains just what I just explained in the actual PowerPoint that we had. We already talked about the QQ plot. This looks at outliers. So I am going towards using when we looked at the plot that we saw before. I think that it's better to use that particular plot because it shows the actual influence and change on the model versus this. It doesn't give quite as much information. So we're going to use that other thing that we showed before that was farther up that looked at the outliers. So this is how you check for the linearity, and this needs to, we made a grid up above. So this is what I had already shown you in the PowerPoint. So it needs to be relatively straight following this dashed line here. So that is how I would create a linear regression model. As I said, you have to run the model and then you can check a lot of those assumptions, just as I just did. Those are the main assumptions you would want to look for. And I've already gone over the coding demo.